Okay, so all of the topics we've done in chapter 9 have been applications of trigonometry. So moving between polar and rectangular form, right, that uses trigonometry. Complex numbers in polar form uses trigonometry. So we have one other topic that is an application of trigonometry here, and that's something called vectors. Now this section 9.4 on vectors is a very, very brief introduction to vectors. In our math department here, we actually have an entire course that's devoted to vectors, and it's usually called linear algebra. Okay, so I'm just going to do very, very basic introduction to vectors here. There's really a lot to cover, and you might see this later on in your other classes. So a vector is a quantity that has both magnitude and direction. Okay, so a vector is a quantity that has both magnitude and direction. So we indicate a vector with an arrow. The arrow shows the direction. And the length shows the magnitude. So this is different than all of the rays we've seen so far in this class. So when we were plotting angles in standard position, we had an initial ray and a terminal ray. Usually in math, this arrow indicates that our ray or our line continues off towards infinity. Here for a vector, this is the entire length of the vector. So if we have two vectors with the same direction and one is shorter than the other, that means the magnitude here is smaller than the magnitude here. Okay, so this is as far as they extend, they don't go off towards infinity. Okay, so lots of things in our real world can be described with vectors. So things like speed of any moving object, right? So if we throw a ball, we might throw a ball in an upwards path. Or if we are driving a car due south, we might be driving a car south. If we're driving that car faster, the length of the arrow would be faster. If we have an airplane taking off, maybe it's steeper with a bigger magnitude. Okay, so speed, which is also velocity, acceleration, all of these things that you see in physics. Force can be represented as a vector. So for example, if you have a box, let's say, and maybe you are pushing the box forward. Now the force that acts on all objects all the time can also be represented by a vector. So what is the most common force that always acts on any object on Earth all at the same time? Gravity. Yeah, so gravity acts in a downward, right? 9.8 meters per second squared, something like that. Force, all these other things can be represented: mass, momentum, energy, work, power, and I'll just put et cetera, et cetera. Okay, so tons of things in our real world can actually be represented by a vector. So all of these words should make you think physics, right? So in physics, you're going to be working with vectors a lot. So other things in our real world that can be modeled with vectors are wind speed. Like in my house, the wind whips from west to east through my backyard. Rain, the direction and magnitude at which rain falls. Tons and tons and tons of stuff. Okay, so this section will just do a brief introduction, and then you'll see this more in your other class. But the whole point of Math 127 is to give you the trigonometric background so that when you get to physics and you start learning about speed, velocity, acceleration, all of these things, you'll remember, like, yeah, I learned all of that in Adrian's trigonometry class. Okay, so in textbooks, we use bold letters to represent vectors. So you'll see like bold V for vector. You might see bold W for a second vector. And if it's a force, you might see a bold letter F. Okay, but of course in handwriting, that's really cumbersome to try and write bold letters over and over and over again. So usually in handwriting, the way we indicate a vector is with a little arrow on top. So we would just write V and then we put this little arrow, and we only put a little half arrow. That's the convention, and it's kind of just out of laziness, so we don't have to draw a whole arrow the whole time. So we'd have V, here's W, here's F with a little half arrow. Sometimes you hear it referred to as hat, like you might hear V hat, W hat, F hat, some other weird things. But so anytime you see this, this indicates a vector, or in a textbook, if you see the bold print, that represents a vector. All right, any questions so far? Okay, so what we want to do now is work on some vector math. And there's two ways of doing this. The first way is graphically. So graphically, I mean with pictures. And when we do this with pictures, it's not precise, right? Obviously, you guys can tell I'm a mediocre artist at best. So what we'll do is we'll do some graphically with pictures, and then what we want to do is come up with a mathematical way to represent a vector. So we can add vectors together, we can subtract vectors, etc. So we can do that precisely. Okay. So first we'll do it with a picture, then we'll come up with a way to represent a vector mathematically, and then we will do the math in a more precise way in just a second. Okay, so here I'm starting with a vector V, and I have a vector W. The first thing I want to do is add these two vectors together. So I'm going to take V plus W. So what I want to do to find V plus W is I start by drawing my vector V. And then at the end of vector V, I'm going to put the beginning of vector W. Okay, so here's V, here's W. So V plus W is the vector that goes from the beginning of V to the end of W. So this green vector is V plus W. Now, you might be wondering, does it matter what order that I put these in? And the answer is no. So V plus W, if I do this in the opposite order, I could draw W first, and then I could draw V. This resultant vector is V plus W, and it should look just like that vector. Oops, I put my little hats on here funny. This is V plus W. Okay, if we want to subtract vectors, we could do it in a similar manner. So let's say we want to do V minus W. What we're going to do is take V and we're going to add it to negative W. So negative W has the same magnitude as W, but the opposite direction. Opposite direction. Okay, so what I'm going to do is I'm going to start by drawing V. So if this is W up here, negative W is going to have the same magnitude, so the same length, but it's going to have the opposite direction. So now what I'm going to do is put negative W onto V here, and the resultant vector, that is V minus W. Okay, so again, what I'm doing here is very imprecise. My drawings are a little bit off, and so we're going to come up with a better way of representing a vector to do this math. The last thing we can do is multiply a vector by a scalar. Okay, so a vector has both magnitude and direction. A scalar is what we call a number that only has magnitude. So this number 2, this is a scalar. It only has magnitude, it does not have direction. Okay, so we can multiply a vector by a scalar. We cannot multiply two vectors together. Mathematically, that doesn't actually make sense. So in order to find 2 times v, you might already think about what this looks like. Here's v, here's a second v, which means this entire thing is 2 times v. And if we wanted to find 3 times v, we would just take something that's 3 times as long. Any questions on this? Okay, so again, this is really imprecise. So what we want to do is come up with something called the position vector. The position vector. And this is going to be an algebraic way of representing a vector. And once we have this, we can do vector math much, much easier. It's kind of like when we started drawing angles and then we wanted to move those angles into standard position so they all looked the same. Instead of having these vectors just float all over our paper, it's helpful to have them all in the same place. So the position vector, what we're going to do is put the initial point of the vector at the origin. So here's some vector v. And instead of just having it float out in space somewhere, we put the initial point at the origin. Now remember, this is the entire vector. It ends right here. So now what we're going to do is we're going to measure 2 things. We're going to measure A, the horizontal component of the vector, and we're going to measure B, the vertical component of the vector. Okay, so A is the horizontal component. And B is the vertical component. What we're going to do now is write this vector v. We're going to write it like this, A comma B. So you'll see, instead of having this with parentheses, right, normally when we have a point x, y, or a, b, we write the ordered pair with parentheses around it. Here we put these little triangles on the ends. This is what represents a vector instead of a point. Okay, so if we have this is just a point. If we have it written in this form, this is a vector. And on your keyboard, if you need to type this in on your homework, you have these little triangles on the last row of your keyboard. Okay, so we'll measure the horizontal component and the vertical component. The other thing that would be really useful to us is to know the length or the magnitude of a vector. So the magnitude of v is the length of v, right? The length represents the magnitude. We denote the magnitude with 2 lines on either side of the vector. Okay, so anytime you see this notation, you can see all of these lines, they look like L's. You can think length, 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 right? There's 4 L's. You can think I need to find the length of my vector v, which is called the magnitude. This one should be really easy for you guys. The magnitude of our vector v. All right, so if we know this side is A and this side is B, what theorem would I use to find this length? What theorem should I use? Shout it out. I know this side is A, this side is B. How do I find this side? Pythagorean theorem, yeah. So this is just a triangle. If we were to draw it in, this side's A, this side's B, this side would be our third side. So this is just going to be the square root of A squared plus B squared. And since we're talking about length, we're only taking the positive, the principal square root here. Okay, so that's nothing new, right? That's just Pythagorean theorem. Any questions so far? Okay. All right, so what we want to do now is figure out how to come up with this position vector for any random vector. So if we take a vector, Okay, so here's a vector. This vector starts at the point x1, y1, and then the ending point is x2, y2. Our question is, how can we come up with the position vector? So for the position vector, we'd need the horizontal component and we'd need the vertical component. So what we want to do is move this so that the initial point is at the origin, and we want to measure the horizontal component A and the vertical component B. Okay, so what we're going to do is we're going to come up with a formula in terms of the starting point and the finish point. Okay, so I want you guys to think about this. So let's think about a really easy one. So if we want to come up with the horizontal component first. So the horizontal component is how far our x values have traveled. So let's come up with a really easy example. Let's say our vector started at x equals 2 and ended at x equals 5. Okay, so along our x-axis, our vector went from 2 to 5. What would A be? What would the horizontal component be? If we start at x is 2 and end at x is 5? 3, yeah. So what we do is we take this ending x value and we just subtract off the starting x value, right? That just tells us how far we've traveled horizontally. So to find our horizontal component, all we're going to do is the ending x value minus the starting x value. Okay, and for the vertical component, it works exactly the same. So let's say, for example, we started at y equals 1 and we ended up at y equals 7. We started at 1, we went to 7. To figure out how far we've traveled, we do 7 minus 1, which is 6. So we'll take our ending minus where we started. So one of my engineering friends told me that the engineering professor here refers to this as tip minus tail. So these are the ending points minus the starting point. So the tip would be the arrow, the tail would be the tail end of the vector. Okay, so tip minus tail. Okay, so let's do an example of coming up with this position vector ourselves. We'll actually have some numbers filled in here and we'll make sure that everything works out. Any questions so far? Okay. So find the position vector V. This is equal to P1, P2 with a hat over it. Okay, so the way this notation is written, oh here, let me write the rest of the problem out for you. If P1 is -1, 2, and P2 is 4, 6. Okay, so we're asked to find the position vector. If our vector goes from P1, so this is showing that P1 is at the tail and P2 is at the tip. So our vector goes from P1 to P2. So the order here is important. This tells us our vector starts at P1 and ends at P2 because this is the arrow's direction. Okay, so this order does matter. Okay, so here's our starting point, here's our ending point, and we're going to come up with the position vector. So let's draw a picture. We can do this algebraically, but I want to draw a picture to make sure everything checks out and to convince you guys that this is indeed what works. Okay, so we have a vector that starts at -1, 2 and ends at 4, 6. Our goal is to move this vector down here so that the tail is at the origin. The starting point is at the origin. Okay, so what we figured out in the last page was that to come up with the position vector, what we would do is x2 minus x1, comma, y2 minus y1, right? The horizontal component, the vertical component. So x2 here is 4, and x1 here is -1. Now remember, all this is asking us is how far we've traveled along the x-axis. What's our horizontal component? We could actually count this out by hand, right? 1, 2, 3, 4, 5. We can actually see that we've moved 5 horizontally, and 4 minus -1 is indeed 5. Okay, y2 minus y1 is going to tell us the vertical component. So y2 here is 6, y1 is 2. In other words, how far we've traveled vertically. So we've gone from 2 to 6, so that's up 4. So we get 5, comma 4. So let's draw on our position vector. So our position vector, if our starting point is at the origin, that tells us our end point is at 5, 4. And this should look like the same vector as this, just shifted down, and it does. So that all checks out. Any questions on this? So it turns out that there's one more way to write a vector aside from this notation. So I want to show you another way of writing a vector, and it depends on the textbook or the professor or the class which notation they use. So our textbook uses both kind of interchangeably, but there is another way to write a vector. Okay, so any vector that has magnitude of 1 we call a unit vector. Okay, so any vector that has a magnitude of 1 we call a unit vector. We have two, so the magnitude of a unit vector, we usually write that as a u, is equal to 1. We have two special unit vectors. So I is our horizontal unit vector. And j is our vertical unit vector. So here's what I and j look like. I is horizontal and has length 1. J is vertical and has length 1. And usually we leave the dots off of the tops of the i's and the j's there and replace them with those little hats. So a vector that we've written up to this point as a comma b can also be written as ai plus bj. So if we go back up to our previous example, here I have a vector written as 5, 4. Or the other way of writing this, I can write it as 5 times I plus 4 times j. These 5s are still our horizontal component. These 4s are still our vertical component. So let's go back up to the picture and see how this makes sense. So if we go back up to this picture of our vector here, if we draw out 5 i's, here's 1i, 2i, 3i, 4i, 5i. So there's 5 times I. And if we add to that 4 times j, so 1j, 2j, 3j, 4j, the resultant vector going from the beginning to the end here is just the vector that we had. So we can actually line up all of these horizontal unit vectors, line up all these vertical unit vectors, and represent our vector in that manner as well. Okay, so two different ways to represent a vector. Like I said, depending on the class or the textbook, you might see them always written this way, you might see them always written this way. Just depends on the textbook and the teacher's preference. Any questions on this? Okay, so let's do one more quick example where we add vectors together, and we'll do them in both of these forms, and we'll see that once we have this position vector written out in either one of these forms, doing vector math is actually pretty simple. So let V equal 2I plus 3J and W equal 3I minus 4J. A will find V plus W, and then we'll do, oh, let me zoom back in, sorry. And B will find 2V minus 3W. Okay, so first one, let's find V plus W. So all I'm gonna do is write out V, which is 2I plus 3J. And then I'm gonna add to that W. So W is 3I minus 4J. All we have to do to add these up is combine like terms, meaning add up the horizontal components and add up the vertical components to get the total horizontal to total vertical. So 2I plus 3I, that's 5I. 3J minus 4J, that's minus 1J. If we wanted to do this in our other notation, V would be 2, 3. And we're adding it to W, which is 3, negative 4. In the same manner, all we have to do is add up the horizontal components and add up the vertical components. And you'll notice these two are the same. We'll do one more here, 2V minus 3W. So I have 2 times V, which is 2I plus 3J, minus 3 times W, which was 3I minus 4J. Okay, so we'll multiply this one out. That gives me 4I plus 6J minus 9I plus 12J, which would give me a total of, add up the horizontal components, so that's minus 5I, add up the vertical components, plus 18J. I'll do it in the other notation for you here, just so you can see what that looks like. In the other notation here, we'd have 2 times 2, 3, minus 3 times 3, negative 4. At this point in this notation, it actually lets you do this a little bit quicker. If you want to write it in one step, you could just see 2 times 2 is 4, minus 9 would give you negative 5. Or if you want to write these all out, we'd have 4, 6, minus 9, negative 12, which would give us 4 minus 9 is negative 5, and 6 minus negative 12 is 18. But actually from this point, if you wanted to jump right down here, right, you'd have 4 minus 9 would give you negative 5. You don't actually need to write out this middle step. Oops, and of course I froze on my very last problem here. Give me 1 second to get this back. Okay, sorry about that. Here's the final answer here. All we would do is multiply this out, add up the horizontal components, 4 minus 9, add up the vertical components, 6 minus negative 12. All right, so today we are continuing with section 9.4, which is on vectors. So let's remind ourselves from last class what a vector is. and then we'll keep working with them. So a vector has both magnitude and direction. Whereas a scalar is just a number, a scalar only has magnitude and no associated direction. Okay, so in last class we saw we represented a vector with an arrow. And this arrow does not continue towards infinity. This is the end of the arrow. So the length of the vector tells the magnitude. And then the direction is given by the arrow. Okay, so this is something that's moving upwards. Here's something that's moving downwards. And if we have something that is a vector that is longer, it has a greater magnitude. Okay, so what we saw last class is we didn't like to have these vectors just floating around all willy-nilly on our paper. So what we did is we took any vector and we oriented it so that its starting point was on the origin. And then what we did is we measured two things. We measured the horizontal component A and the vertical component B. And here I've drawn a vector that goes into the fourth quadrant just to give it something a little different look from the last class. Okay, so here's our vector V. So we saw last class there's two different ways we can denote a vector here. We can either write that vector V is equal to the horizontal component, comma, the vertical component. And what we do is we put these in these little triangles. That's what indicates that it's a vector rather than an ordered pair or a point. Okay, then what we also saw at the end of last class is we can also write it as the sum of multiples of its horizontal and vertical unit vectors. So we could also write it as AI plus BJ, where I is the unit vector in the horizontal direction and J is the unit vector in the vertical direction. Okay, so two different ways to write a vector, and we did a little bit of vector math last class. Okay, so one of the questions you'll be asked in physics, and I distinctly remember this from being in college physics and not getting why they cared so much about unit vectors, but one of the questions you might be asked is to find a unit vector in the same direction as a vector. So let me go over this and explain why this is important. So find a unit vector Okay, so to find a unit vector in the same direction as a vector V, what we want to do is look at this vector V, and we want to find a vector that has length 1. So it might look something like this, but that's in the same direction. Okay, and I'll explain in a minute why this is important, why we want to do this. Okay, so to find a unit vector in the same direction as our vector, what we do is we take this vector. So our unit vector is equal to our vector. Now think about this. Let's say this vector has length 5, just for example, if this vector has length 5, and we want to find a vector that has length 1. Okay, so if this vector, for example, has length 5 and we want to find a vector that has only length 1, I should take this vector and divide by what? 5, yeah. How about if this vector has length 7 and I want to find a vector in the same direction that only has length 1? I should take this vector and divide by 7. So all I have to do to find a unit vector in the same direction as a vector is take the vector and divide by the magnitude of the vector. So remember from last lecture, this means magnitude. Those two vertical lines. So the way you can remember this is when you see these lines, you should think they look like an L, right? L, 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 L. That's the length of the vector. The length of the vector tells the magnitude. Okay, so let's go ahead and give this a try. Let's find a unit vector. In the same direction as 4i minus 3j. So we just saw from up above, to find a unit vector in the same direction, we're going to take our vector and divide by the magnitude of the vector. So in order to divide by the magnitude of the vector, the first thing we should do is actually find the magnitude of the vector. So remember, the magnitude of the vector is just the length, and if the horizontal component is 4 and the vertical component is -3, all we have to do is use Pythagorean theorem here, and we get that the magnitude is just a squared, the square root of a squared plus b squared. So we have the square root, 4 squared is 16, -3 squared is 9, so 16 plus 9 is 25, and we get that the magnitude here is 5. And we could draw a picture just to make sure everything looks good. So this tells us our horizontal component is 4 and our vertical component is -3. So our vector looks like this. And the magnitude is 5? Absolutely, right? There's our good old 3, 4, 5 triangle. Okay, so now we can plug this into our formula. So what we're going to do is take our vector, which is 4i minus 3j, and we're going to divide by the magnitude, which is 5. Now, we should always write a vector in the form ai plus bj, so we can't leave it like this. We want to have the fractions as coefficients in front of the I and as coefficients in front of the j. So the next thing I'll do is do this division. So I have 4/5 I minus 3/5 j. So this is our answer. So again, we should always write this in the form ai plus bj, or if we're in that other notation with the little triangles on the sides, we could do that. So let's look at our picture and make sure that this makes sense. So 4/5 is probably right about here. Minus 3/5 is probably right about here. So the unit vector in the same direction looks like that. Yeah, we're in the right direction. And that, as far as scale goes, looks about right? We figured out this length was 5. So if we split this up into fifths, looks great. Any questions on this? Now, what I remember from high school physics and college physics was that they asked me in this physics 1 class, like, find a unit vector in the same direction, find a unit vector, and they asked it over and over and over again. And what I couldn't wrap my head around when I was in college is why? Why do we even care about this? What's the point? So let me tell you why this is important and why you might see this come up in your other classes. So, why do we care? Since the unit vector is equal to the vector divided by the magnitude of the vector, right? That's just what we saw on the last page. That means that, this is the important part here, this magnitude of the vector, this is a scalar. Scalar is just a number. So in the last example, it was the number 5, which means we can multiply both sides of the equation by a scalar, right? We can multiply both sides by 5. So that means that a vector can be written as its magnitude times a unit vector in the same direction. Okay, so why do we care about finding a unit vector in the direction of a vector? Because of this. So this is the important outcome. A vector can be broken up into its magnitude times a unit vector in the same direction. So we can find and this is particularly helpful in the real world. For example, when it is really windy at my house, usually weather apps will say the winds are moving 30 miles per hour in a northeast direction, right? So that's the magnitude, 30 miles per hour in a northeast direction, that's the direction. Usually we don't see on the weather apps or in the real world, the vector representing the wind is 16I plus 42J, right? Those things don't really come up in the real world. So in the real world, they usually tell us our magnitude in the direction. So also like cars, right? If a car is moving, it might be moving 65 miles per hour. in a south direction. That's usually how we describe things. But in order to do vector math, we need to have it in this vector notation. Okay, so now here's the big conclusion. So again, this whole chapter 9 is applications of trigonometry. So how does this relate to what we've been doing for the last 3 or 4 chapters? Okay, so here is a vector v. Here is a unit vector in the same direction as my vector v. So again, same direction, but it has length 1. All right. We'll call this angle alpha. If I drop a perpendicular from the unit vector down to my x-axis, forming a triangle, I have that because this is a unit vector, this side has length 1. That means, and here's A, our horizontal component, and B, our vertical component. Okay, if we look at A, that's our adjacent side, and 1's our hypotenuse. Okay, so cosine of alpha would be adjacent over hypotenuse, but hypotenuse is just 1. That means that A is equal to cosine of alpha. If we look at just B, this is the opposite. This is the hypotenuse. So sine of alpha would be opposite over hypotenuse. So sine of alpha would just be B. So that means B is equal to sine of alpha. Okay, so here's our big conclusion and how it relates to trig. That means if we have a vector v, we know we can write that as its magnitude times a unit vector in its direction. So we have the magnitude, and then the unit vector is just, this unit vector is just our horizontal component of it is cosine alpha, and its vertical component is sine of alpha. So the unit vector is given by cosine alpha I plus sine of alpha j. Okay, so this is the big conclusion here. So this is what you'll see a ton in physics and engineering classes, I promise. And I'll do 1, 2, 3 examples using this formula. And I remember struggling in physics, like how do I remember which one goes where? And this is exactly the same as we've done all semester. So x, or the horizontal component, goes with cosine, and then our vertical component goes with y or sine, right? So they go in alphabetical order. So if that helps you remember, I and j are in alphabetical order, cosine, sine are in alphabetical order, there's a good way to remember it. Any questions so far? Okay, so I will do, what did I say, 3 examples using this formula and show you how it works. Write the vector v in the form ai plus bj, given that the magnitude of v is 31 and the angle it makes with the positive x-axis is 210 degrees. Okay, so we'll start by drawing a picture, and then we'll plug everything into our formula and see what we get, and we'll verify from our picture that it looks correct. Okay, so first thing we have is that we have a vector, and the angle it makes with a positive x-axis. So here's a positive x-axis is 210. So 210 is 180 plus 30. So here's 210. The next thing we're told is the magnitude is 31. So remember here, this vector, the length of it tells the magnitude. So I'm just going to put a 31 here to indicate that's how long it is. So we want to come up with a vector in the form AI plus BJ. So we know that we can write a vector as its magnitude times the unit vector in the same direction, which is given by cosine of alpha I plus sine of alpha j. So the magnitude is 31. Alpha in this example is 210. All right, so on this next step, we want to evaluate cosine of 210 and sine of 210. So you have two options. The first is, of course, use a calculator since you're allowed one on exam 3. But if you'd like to do it by hand, all we have to do is draw a quick picture of 210. We know this angle is 30. So our sides are 1, root 3, and 2. So we can fill this in easily by hand. So cosine is root 3 over 2, and cosine in the third quadrant is negative. Sine is 1 over 2, and sine in the third quadrant is negative. So filling those in by hand, I get negative root 3 over 2 I plus negative 1/2 j. We're asked to write this in the form AI plus BJ, so we should take one more step here, and we should multiply this out, distribute that to both of the terms. So we get negative 31 root 3 over 2I minus 31 over 2j. And it is standard to put these numbers out in front of the i's and the j's and to not have the I say in the numerator there. So to have these separate. So these are coefficients, so this should be out in front. So somebody asks, could we write it like 31 cosine 210 sine of 210, or does that mess things up with the plus? So the question was, what about putting this in the other notation? So our other notation, instead of AI plus BJ, right, our other notation was A comma B, like that. And so the question was, can we use this other notation for this problem? On your homework, if they specifically ask you to put it in the form AI plus BJ, you need to use this form AI plus BJ. In my experience, this is more common than this notation, but absolutely, once you get to your final answer, you could write it like, so his question was, can we do it up here? Sure, you could have done that in the first step and use this other notation. Absolutely, if you wanted to. Any questions on this one? Okay, let's do 2 more examples. And I remember from physics classes and tests, the question that got asked over and over and over again was, if there was more than one force acting on an object, what was the resultant force vector? So first we'll find a force vector of just one force acting on an object, and then we'll find a resultant force on the next example with 2 forces acting on something. So like I remember from being in college physics, like if there was a hill and you were pushing a box up a hill at a particular angle and gravity was pulling it downward, things like that, what's the resultant force? Okay, so that's what we're building up to. I got 2 more examples here. One will do something with 1 force and one will do something with 2 forces. I did not put any physics types problems on your exam, but you do have a couple of simpler questions from this section. Okay, so a child pulls a wagon with a force of 25 pounds. The handle of the wagon makes a 45-degree angle. with the ground. Express the force vector in terms, oops, sorry. Of I and J. Okay, so child pulls a wagon with a force at 25 pounds. The handle of the wagon makes a 45-degree angle with the ground. Express the force vector F in terms of I and J. Okay, so let's draw a picture. Okay, we have a angle of 45 degrees, and the force is 25 pounds. So our goal is to come up with the force vector in terms of I and J, its horizontal and vertical components. So this one, you might actually be able to guess the answer without doing all of the work, since a 45-degree angle is something we've worked over and over and over with this semester. So if you can guess the answer, great. Go ahead and follow along with my math. I'll do this the long way, and we'll make sure that everything looks good. So our vector here is given by F instead of V, which is fine. Lots of times forces are given as F. So this is equal to the magnitude of the vector times cosine alpha I plus sine of alpha J. So again, easy way to remember this, I and J go in alphabetical order. Cosine and sine also go in alphabetical order. So now we just fill these things in. So the magnitude was 25 pounds and our angle was 45. Okay, so we know from all of our work this semester that cosine of 45 is 1 over root 2, or rationalizing here just to make this easier, root 2 over 2. Sine of 45 is also root 2 over 2. Last step, multiply this out, so we get 25 root 2 over 2i plus 25 root 2 over 2j. Again, we should always put it in the form AI plus BJ. So we want these coefficients to be out in front of the I's and the J's. Okay, next question I had in this chat was, when do you take physics? You guys are all taking it next semester? I think most people are taking physics next semester. All right, any questions on this problem? Any questions on this problem? Oh, we should look at our picture and make sure that this looks correct, right? So obviously this root 2 over 2, right? We know in this 45, 45, 90 triangle that these sides, this comes from sine and cosine of 45. So we expect this. But how to check if these numbers actually make sense? So root 2 is about 1.4. So what I would think is like 1.4 over 2, that's going to be, you know, less than 1. So this is going to be smaller than 25. This is smaller than 25. These two are the same. So yeah, that looks about right? We want to make sure that the magnitude is right. We want to make sure the positive, negative values are right. And then of course we could check Pythagorean theorem with these three numbers if we wanted to. But yeah, that looks good. Any questions? Okay, one more, last one. Two forces of magnitude 60 newtons. So a newton is a measure of force. So 60 newtons and 70 newtons act on an object at angles of 30 degrees and negative 45 degrees. Find the resultant force. Okay, so this is very representative of something you might see in your first semester of physics. Okay, so let's draw a picture and figure this out. So we have the first force that has magnitude of 60 and is at an angle of 30 degrees. So here's 30 degrees, and this one has magnitude of 60, and I'm going to call this force 1. Our next force acts at a negative 45 degree angle and has length 70, so I'll make that a little bit longer, and I'm going to call this force 2. Okay, so our question is to find the resultant force. So to find the resultant force, what we're going to do is we're going to add up all of the forces that are acting on an object. And when you're in physics, usually you'll have some force being acted on an object by an external something, and then you'll also have gravity you should usually always account for. So my guess is, looking at these two vectors, the resultant force, right, the direction should be somewhere in between here. And it's going to look something like that. There's my educated guess. Let's figure out what this is exactly, and we will see if our guess is right. So this is F1 plus F2 in green. That's my guess. Okay, so what we want to do is take two steps. First, I want to find the vector representation of F1. Then I'm going to do the same thing over here for F2. Then once I find how to represent these two, I'm going to add them up. So then I'm going to find F1 plus F2. Okay, so F1 is going to be the magnitude of F1 times cosine of, I'm going to call this alpha, plus sine of alpha j. Okay, so our magnitude for force 1 was 60. And then we have cosine of 30 degrees times I plus sine of 30 degrees times j. Okay, so we know how to find cosine of 30 and sine of 30 really easily. We've been doing this all semester, so that's root 3 over 2. And sine of 30 is 1/2. Last step, multiply this out, and we will reduce as we go. So 60 over 2 is 30, so we get 30 root 3i plus 30j. We should at least take a look at our picture and make sure that this makes sense. So this is saying that the vertical component is 30, and the horizontal component here is 30 root 3. Root 3 is about 1.7 something, so yeah, that looks good. You could check Pythagorean Theorem, but at a minimum, what you want to check is that the scale is about right, and then you should check that we're in the first quadrant, so these should both be positive. So that looks good. Okay, so we're going to do the same thing with force 2, and then we'll add them up. So force 2 is equal to the magnitude of force 2, I'll call this beta, times sine of beta I, I'm sorry, I wrote this backwards, cosine of beta I plus sine of beta j. So we got 70 times cosine of negative 45 plus sine of negative 45 j. Okay, so we know cosine of negative 45, we know that's root 2 over 2. Cosine's positive in the fourth quadrant. And sine of negative 5, we know that is negative root 2 over 2. Sine in the fourth quadrant is negative. Next step, we'll multiply these out. So I got 35 root 2i minus 35 root 2j. We should check that this looks good on our picture. So here's our vector we're looking at. We got that our horizontal component was 35 root 2 and the vertical component was negative 35 root 2. So that's right? We're in the fourth quadrant, so x is positive, y is negative. All right, so force 1 plus force 2, the resultant force, what we want to do is add all of these up. So I'm going to take 30 root 3i plus 30j. right? There's force 1, and I'm going to add that to 35 root 2I minus 35 root 2J. So let's add up our horizontal components. So our horizontal component is going to be 30 root 3 plus 35 root 2I. Then we'll add up our vertical component. So I have a 30 and a minus 35 root 2. J. Now, this is the exact answer. If you can simplify, you should. Usually what's more helpful to us is an approximate answer, so we can actually visualize what these numbers are. So if we put this in a calculator, this one comes out to 101.46I, and then we have minus 19.50J. So the last thing we should do is look at our picture and make sure that this makes sense. So our resultant force, force 1 plus force 2, the horizontal component was 101, that looks good. And the vertical component was about negative 19, looks great. Okay, so this is very, very representative of what you might see in physics. And hopefully I gave you guys a good introduction on vector, so when you see this again, it makes more sense. I wish I could go back to college physics and kick its ass now that I know how to do this, now that I've been teaching this class for over a decade. But yeah, I won't put problems like this on your exam. You will see problems like this on your homework. There's a couple just for you guys to get some practice. But I know some of you aren't moving on to physics, so I definitely did not put anything like this on your exam.